Let's try to estimate how fast something can spin without spinning itself to pieces. So let's assume we have a spherical something with a mass, let's give it a solar mass roughly to get some specific numbers, and it's rotating with a particular period p. So p is how long it takes to spin around once. Now if we look at something on the surface, so here it's spinning round, something on the surface, the question is, can it stay on the surface or will it get flung off to space by the rotation? Now this object is going to have a downward gravitational force, and there is going to be an upward normal force from the surface. And it's moving in a circle of radius r. Now we know that for anything to move in a circle at radius r at some velocity v, there has to be a net force towards the middle, a centripetal force, of mv squared over r, where m is the mass of this whatever it is sitting on the surface. Now in that case, that'll be contributed by the difference between the gravitational force and the normal force. If something's spinning very slowly, the gravitational force and the normal force will be equal and opposite, so as to leave the object lying on the surface. If it's spinning faster, the normal force will be reduced, but the gravitational force will stay strong. As it spins faster and faster and faster, the normal force will shrink away to zero, so at the crucial moment when something's about to be hurled off the surface, the gravitational force all by itself, with no normal force taken off it, is supplying the centrifugal force. If something spins even faster still, then it will have to fly off into space. Normal force can't pull down unless something's watered down. So if something is spinning such that gravity cannot supply the centripetal force, it must fly off. So at the critical dividing line, when things are just about to spin off, we'll set that equal to the gravity, given by the normal equation. Okay, so that's telling us at balance this is going to happen. Now we also know what the velocity is. We know the period. Now the velocity, it's got to go all the way around every period. So the distance it travels, 2 pi times the radius, that's the circumference of the circle, divided by the velocity, it's got to be equal to the period, which means that the velocity equals 2 pi r over p. Now let's plug that into here. We end up with v squared, so it's going to be 4 pi squared r squared over p squared, and then we've got the 1 over r equals g mass of the whole object, which is the mass of the sun, mass of the lump on the surface, over r squared. Now what can we do here? Well, the mass of the lump cancels out. That cancels with one of these. We put that r up to that side. So we end up that I have r cubed over here equals g m sun, p squared moves up to the top, and the 4 pi squared moves down to the bottom. And we can then take the cube root, and we get that r equals cube root g m p period squared over 4 pi squared. Now for the first pulsar, we know the period is about a second. So if we put 1 second into here and we assume it's got the mass, something like the mass of the sun, we find out that this critical radius comes out as about 1500 kilometers. Now bear in mind that is an upper limit. If it gets bigger, the centripetal force is larger, gravity gets weaker, so the centripetal force will be much bigger than gravity, so things will fly off. But it could be much, much smaller than this. What's interesting about this number is that it's smaller than the size of a white dwarf, which is, if you remember, about 5,000 or 6,000 kilometers. So what this is telling us is that a white dwarf cannot spin where it goes around like every second or so. It just can't spin that fast. The surface layer will be flung off into space. So we have to be looking at something here which is smaller and denser than a white dwarf.